Okay, so I'm going to actually run the cluster analysis now. First, I'll talk a little bit about my data. Schmidt, Chapman, and Jones found that companies that focus their recruitment advertisements on applicants' needs attract more qualified candidates than companies who focus on abilities. There are 3 job design characteristics that affect applicant attitudes and their decisions to apply. This would be job motivators like skill variety, autonomy, career advancement, social components like feedback, social support, and work-life balance, and work context like physical needs and job security. So that being said, an organization wants to understand the types of people who are continuing on in the selection process within their company and the types of people who are likely to apply. They have good reason to believe that there are a few different groups of people applying, and they're considering designing their recruitment strategies to better attract certain types of candidates. The series of questions on the survey data here are geared towards job motivators, social components, and work context, and answered by candidates. The organization wants to know who is likely to recommend the application process to others or choose to continue the application process. So here's that data, all continuous. Employee ID is actually candidate ID. I just didn't change the variable after I changed my data. So anyways, hang on. Yes, babe, I'm recording a video. Hurry.
How do I connect Bluetooth?
I don't know how to do it on your phone.
How do I get it on your car to pop up?
You click the center button.
Okay, sounds good. Bye.
Bye. Okay, sorry. Okay. I'm going to first attach the data with the attach function. Then I'm going to load in the rattle function, which is the R analytic tool to learn easily. And it actually provides a collection of utilities functions for graphing, which we're going to need to see the clusters. The head function is going to return the first rows of a matrix or a data frame. So here we can see the first 6 rows of the data. The following syntax is going to standardize the variables using the function scale. Then we're going to we're going to use the k-means function. This is where you actually specify the number of clusters. You might have to run this a couple of times, like to see which one is best. I'm not going to do that on the actual video, but I promise you that I ran this several times. And I think that a cluster, or I think a cluster model of 2 is going to work best. But basically, this is where you can go back right here and specify like how many clusters you want, which is one of the main components of the k-means clustering method. This is just the attributes, like what is contained within, like the names of it, like all that stuff that you use. I think I don't really know for sure that it was hard to find. This is going to give a matrix of center clusters. The cluster means matrix has the cluster numbers from 1 to 2. Oh my gosh, sorry, my phone's getting blown up right now. And the variables are across the top. So these are the items right here. This is like their likelihood to recommend the hiring process. And these are the cluster numbers right here. So we have 2 clusters. This syntax right here is a vector of integers indicating the cluster to which each point is allocated. So the clustering vector is a vector of integers indicating the cluster to which each point is in. So we see that. Here we get the cluster size. This is the number of points in each cluster, so each cluster has 60 points in it. basically tells you how many observations are in each cluster. The set seed is going to guarantee that the results are reproducible. This is where you specify the number of iterations. This is going to help us generate the graph to find the optimal value of clusters. Again, like, I'm pretty sure that the number of clusters is 2. You could go back and do this many times, which I have, but again, I'm not putting that, like, in the video right now, because it would be a while. Okay, so there we set the seed. So the next part of the syntax is going to generate the elbow chart. The K-max part specifies the max number of clusters to appear in the chart. Data specifies the data frame. I want to use the standardized data here, not the original format data. The format of the k-means function in R is right here. This is it. This is pretty much it right there. We see those attributes coming in again right here in several of these. X is a numeric data set. The matrix or the data frame. And then within the function. Okay, so that's beside, it's X comma centers. Okay, yeah, so like right here. And then it centers is the number of clusters to extract. N star is how many random sets should be chosen. This clustering approach can be sensitive to the initial selection of centroids. The k-means function has an n-start option that attempts multiple initial configurations and reports on the best one, and this is the recommended approach for the k-means method of cluster analysis. The elbow method is going to be used here. There's many methods that you can use to get an idea of the number of clusters. This is kind of like, again, what you do in factor analysis when you get the elbow chart. So this is all of it for the elbow chart. Okay. So here we see that it starts dropping at 2. So that's the amount of clusters that we have. An elbow chart plots the within group sums of squares versus the number of clusters extracted. So based on this chart, there's a distinct drop in within group sum of squares when moving from 2 to 3 clusters. So after 2, this decrease drops off, suggesting that a 2-cluster solution may be a good fit to the data. Okay, so now that we have that, we can run the solution with that earlier syntax where we specified 2, where we made that k-means fit model right here. That's what's going to be used in this syntax. The cluster function in the library is going to be used to cluster the solution into 2 dimensions. The next part of the syntax is going to generate the plot. The CAD.stand is an object that we created, or that I created. Main equals is the title for the plot using the $call function, so attaching that to the function. We have 2 labels specified and no lines. Yes, I have a cough again. Please don't ask why, because I was showing you the answer, but I'm pretty sure that I might just be dying. So, okay, so here we have the plot. We see that it fits very nicely into 2 clusters. The cluster labels are here. The reason why the numbers are basically overlapping each other is because how I did my data. It kind of took me like a second to figure this out, but it's because like I copied and pasted my data and kept doing it. So like a lot of the data points are literally exactly the same for a number of variables. Okay. So basically this plot gives us a different type of visualization for the solution. As you can see, there are 2 distinct groups here. It takes the k-means results in the original data as arguments in the function. And in the resulting plot, observations are represented by points using principal components if the number of variables is greater than 2, which obviously it is. It's also possible to draw concentration ellipses around each cluster, which I did here. The fact that the two-component solution is best means that two components can explain the majority of variance. So here it explains 77% of the variance. So moving on, if I don't die before I get to the next part. So next we have to figure out how well the k-means clustering uncovered the actual structure of the data obtained in the type, or in the, what did I call it? Likely variable. A cross-tabulation of ID and cluster membership is given by the following syntax. Oh, I mean likelihood, sorry. Okay. Now we can print that output. And then we can quantify the agreement between likelihood and cluster using an adjusted rank index provided by the FlexClust package. The RAND index is on a scale from -1 to 1, 1 being perfect fit and -1 being not a good fit at all. So loading in the FlexClust, specifying the ct.kn. So we got a 0.39, which is kind of okay. I'm not using this anymore. And so, yeah, it's basically telling us that there are two clusters here. It doesn't tell you why the clusters are there, but it tells you how many there are.